All right, this is going to be assignment for case 2 for flow moving over a half a cylinder. This specific part of case 2 is going to be the viscous turbulent flow. So first and foremost, we'll go over the geometry. I actually had to change this up a little bit just because there was some issues with the surface to sketch. Before I was making the rectangle much larger, trying to think to expand this area so that I could get the results more accurate. However, because this is the student version, I wasn't able to do that, and I had to maintain a smaller system for this to be analyzed in. So first, like the other method, just want to go to XY plane, and to do your sketch, you go to the sketching. Again, the same as before, you draw your rectangle, like so. You then can go to dimensions, click general, drag up and across from each of your sides, and then you will be able to go into your details view and get your dimensions. For the height, I chose 400. Anything over 400 seems to get a little bit buggy, and the surface to sketch won't work as efficiently. And the same with the height. I just did as 160 just to keep things, again, simplified. And it seems from the results that this was it was okay to use this system size. Following that, we had to get a circle with a diameter of 20, but not just a circle, a half a circle. So in order to do this, all I did was I drew a circle here, and I put it on the x-axis, and I drew just a circle like this. And then I was able to go to the Modify tool, click Trim, and then when you zoom in, you can actually trim the outside of the circle and trim the 2 radii of this part here. So this is just like an open gap. In order to actually get the dimensions proper, you can either use radius or diameter, or you can use general. You click and drag downwards, and it'll give you the diameter of the circle, which essentially would be 20 meters. So once that's completed, again, we're going to move on to our meshing stage, just like before. Here, I already have the mesh set up. Different from case 1, I decided to go with a triangles method because I seemed to get more accurate results and the solution converged faster than the quadrilateral dominant. So I first went into insert, method, and again, I got the triangles method. You can switch that here between quadrilateral and triangles. Once this was done, I went to mesh and I adjusted the size to 1 meter element size. And this is the mesh you see now. I originally was going to go for refinement level 2 or level 1, but because this is the student version of ANSYS, I am not allowed to have that many meshing components in my mesh. So I just left it as the triangles method. Like the other situations before, we also had to make our name selections. Our inlet flows coming from the left, moving to the right to the outlet. Dismiss that. Our symmetry is the top and the bottom between here, and our wall we're just going to use as the cylinder or the edge of the circle right here, the half circle. And that's where we're going to be calculating our lift and drag coefficients. So moving on from the meshing, we can go to our setup here, which again has already been completed. I'm just going to go over the initial setup. So because this is going to be viscous turbulent, we want to make sure we're on, obviously in the viscous, but we want to choose the proper turbulent model. So I did that. Standard wall functions will be fine for this. That's okay. Next, we have to go to boundary conditions. And this is where we have to actually do a little bit of calculations because we want a specific Reynolds number. We want a Reynolds number over 1 million. As specified previously in the lecture. In order to have that, we need to modify our velocity and our viscosity. So after a little bit of calculating, I came to the conclusion that if we wanted to have a Reynolds number over 1 million, we want to have a 7.35 times 10 to the negative 4 viscosity value and a value of 70 meters per second for the velocity. And again, that's going to be just over 1 million, so that would put us in the turbulent range. Clicking OK with that. Everything here can stay the same because the system's smart enough to know that this is a wall and such. Reference values, make sure, again, we're computing from inlet. This viscosity, it just changed. All the results here have been based off my other viscosity. Let me actually go back. Dynamic, no. Reference values. Let me go to surface body maybe. Hold on 1 second. Interior surface body. Inlet. Okay. Well, anyways, you want to change your area to the area of the half circle. So it would be 1/2 pi over 4 times diameter squared, which would yield 39.27 meters squared. Again, velocity 7 meters per second, and this should be changed to 7.35 e to the -4. Again, my calculations did already incorporated that. I will run them again because I know they converge relatively quickly. I believe it's in the first minute or so. So I'll let that initialize really quick. In the console, initialization is complete. And then I'll run the calculation to 500 iterations, though I believe it only converges in approximately 70, and it iterates quite fast. So let's take a look here. Yeah, so we can already see that it's converging relatively fast compared to some of the other ones we've done. And again, that's due to the triangulated mesh we did, and for some reason that seems to work better for convergence for the specific case. For the other two parts of case 2, I also use triangulated meshes with the same setup as currently, except again, I'm changing the inviscid flow and the laminar viscous flow. So we'll let that iterate for a second. Should take another about a minute approximately. Feel free to skip through if you don't want to watch this. I've watched it a couple times. I'm just recalculating it just to make sure that the values are accurate. Like I said, I believe it converges in 70 from the last time I ran it. Oh, much less actually. I believe it converged. Calculation complete. Beautiful. As you saw before, all the plots popped up. That's because I already went ahead and did them before. So really quickly, just showing you the velocity contour, just so you can get an idea of what we're looking at here. Your typical contour looking. As you can see with turbulent flow, we have a little bit of unsteady flow in the back area. It's not as uniform as it originally was with the laminar viscous flow because we increased our velocity. Our CP contour, we'll pop that up really quickly. CP contour is looking very similar to the laminar flow. Again, it's going to vary between 1 and -3, or we should expect it to, with some variation. And let's go to our CP plot really quickly. And when we look at it, as we go along the curve length around the outside of the half cylinder, again, this is along the circumference of the outside of the half cylinder. So starting off from the left and kind of moving along to the right, this is where we're going to see our variation between about -3 and about +1, just about, which again is expected. So next we can go and see our lift and drag coefficients by going to the reports tab, going to forces. First we will check we'll do lift coefficient first just because that's already there. We'll go to console, take out these, and our lift coefficient is actually right down here. It would be a total of 0.758722214. And we can tell it's the coefficient for lift because it's in the y direction. Next, we will go to the drag coefficient. We'll put this direction of 1, and we'll print those results out really quickly. And as you can see down here, this is our drag coefficient. So because we have turbulent flow and because we're over like the half cylinder rather than the full cylinder, we would have less drag than compared to when we just had that full cylinder in the middle of the tunnel. So again, that's also expected. But yes, that does conclude this portion of the project, and thank you so much for watching.